So let's see. So we were talking about this regime diagram, and we looked at how the different quantities here could be expressed if we plot it like this. And I tried to construct it here, and here you see how it looks like. And see here they don't even show the Damköhler in one line. And so you see this is here the Reynolds number equal to 1, laminar flames, and all this here would then be turbulence. There is this Karlowitz equal to 1 line. That is a very, very important line, and because that essentially for Karlowitz more than 1, the flame is thinner than even the smallest case of the turbulence. And that means, you could say in the limit, then for the turbulence, the flame looks as if it is infinitely thin. Okay? So sometimes before we made the assumption, we said, okay, let's assume the flame is infinitely thin and so on. And that always means in comparison with the smallest case of turbulence. And in this regime, that is actually a good assumption. And you see here that this regime here is actually separated again in two parts. One is called here the corrugated, one the wrinkled flameless regime. The wrinkled flameless regime is not all that important because it's technically not very relevant, because what you see here is that the burning velocity in that regime is larger than the turbulent velocity fluctuations. And it turns out that if that's the case, then the turbulent velocity fluctuations, they try to do this. They try to, kind of wrinkle this thing. But the flame burns much faster than the turbulence can wrinkle the flame, and so it will never be wrinkled. Okay, and so well, why it's still called the wrinkled flameless regime, I don't know. But the idea is that there's not much wrinkling there. Maybe wrinkled means it's not much corrugated or whatever. But okay, so that's the point. So we won't talk about this much more. And you see here the distinguishing line is V prime over SL equal 1, meaning that in this regime here, V prime gets very small. Okay, so you should look at this here as the corrugated flameless regime, where this here is just an extra distinction. This I mentioned is an important line. Now, if you are above this line, then it turns out the turbulence can actually enter the flame structure, and it can do so, it can cause mixing in that flame structure. However, if the turbulence scales are smaller than the flame thickness or the preheat zone thickness, but they're still larger than the reaction zone thickness, like what we're discussing here, then the reaction zone is still undisturbed. Okay? Then turbulent mixing will help in the preheat region. Remember, the preheat region, all it does, it tries to cause transport and to make the to preheat the gases so that chemistry can happen. And so in that regime, then the turbulence helps to make the chemistry to make that transport a little faster, but it does not disturb the structure of the reaction zone. Okay. So that is what you have in between these two, and because in this regime the reaction zone is still thin compared with the turbulence, we call this the thin reaction zone regime. Okay, so this is here. Now, if you make the turbulence scales then smaller and smaller, then if the Kolmogorov scale becomes even smaller than the thickness of the reaction zone, then it will even disturb and mix up the reaction zone, and we call this the broken reaction zone regime. Okay, so this is in a nutshell what the physics in these regimes are. And that's all described here. On the left is the Reynolds number, wrinkled regime, broken reaction zones. And so what's said here also is that we won't talk much about broken reaction zones regime. We won't talk much about the wrinkled flamelet regime, except for what I just said anyways. Okay, so the corrugated flamelet regime, maybe I mentioned these things here. Karlovitz smaller 1, which means 11 is smaller than Kolmogorov scale. And in that regime then, the flame is quasi-laminar on the scales of the flame, and the flame is entirely embedded into the turbulence. And so if you go to these larger or smaller or larger flame thickness or smaller Kolmogorov scale, then you cross this Karlovitz equal 1 line. The only thing I didn't say, is that this is also called Klimov-Williams criterion. Okay, so this line here is called the Klimov-Williams criterion, just in case you ever hear this term mentioned somewhere. Okay, I think I explained the rest of this. The reaction zones regime here also, I mentioned this. This comes when Kolmogorov scale is smaller than the flame thickness, but still larger than the inner layer thickness. And this happens here at about Karlovitz equal to 100. I said this earlier. And yeah. Sounds funny. Doesn't work. Then battery. We had this yesterday on. Replace the battery in 1.
It's on its way.
So let's see if that works. Does this work? Yeah. Okay. Good. So we should tell that guy to replace the other batteries also later on. Okay, so what was I saying? Yeah. Okay, so where was I? Right, was it just trying to go back? Oh yeah, to show you something. Okay, I wanted to show you something here, and I can't remember. Oh yeah. So this here, this is Karlovitz equal to 1. Okay, this Karlovitz delta equal to 1. This here would be Karlovitz equal to 100. But keep in mind that 100, that's just because we said the inner layer thickness is, a tenth of the flame thickness, and that comes from just looking at methane flames, and so it's it's a rough estimate for certain conditions. Keep in mind that this line, it might move up or down a little bit depending on what the conditions are, and depending on what the fuel is. But so this here is a rough estimate, where all the others, they kind of come out of the scaling directly. That's what I wanted to show you. Okay, so in the corrugated flamelet regime, then there is the, and here I just want to mention this. Length scale. I don't think it's of much relevance, but there is the so-called Gibson scale, and the Gibson scale is the length scale at which the length scale that's associated here with this line. Okay, so the Gibson scale is that's the length scale of the turbulent eddy where V prime is just equal to Z. Okay, and so if the turbulence then becomes of smaller length scale, then it can't do anything, or becomes slower, then it can't do anything. So again, because this whole regime and also the transition from here is not very important, then it also does, technically not very important. But even so, it's even if it is important for the case you're looking at, the physical differences in these regimes are not very large. The Gibson scale, even though you might hear that term sometime, is not of great relevance. Okay, so this here just shows, this just shows the Gibson scale, and I want to skip this. I want to skip this also. This is a more interesting point here to make, and I'll come back to the previous slide. But now what we said is, in the thin reaction zones regime, the length scales of the turbulence, they're smaller than the flame thickness, and because of that, they can actually penetrate that flame thickness and the preheat zone, and they can cause turbulent mixing. And this is an example here. This is an eddy here that has the same time scale as the flame time scale, so it can interact with this. It can cause mixing here. And you see that takes some of the hot fluid. So this here is supposedly the preheat zone. This line here is the reaction zone. And so you see this here, the reaction zone, it cannot cause any mixing in the reaction zone. It can just wrinkle this reaction zone around. However, it can take stuff here out of the preheat zone, hot material, and move that to some region ahead of the flame. Okay? And then, you have some turbulence that might mix it up, might mix this up, or you have diffusion, and then that causes a faster transport of hot fluid ahead of the flame. Okay? And what's interesting is that by doing that, also you get a larger preheat zone thickness. Okay? And so the question could be, what is the thickness then of this new preheat zone thickness that is thickened by the turbulence? And that's, we want to call this thickness here Lm. And there's some scaling arguments that give you that thickness, because that's eddy. So you have a whole spectrum of eddies now. You have the Kolmogorov scale, and you have larger scale, and you have very large scale. And it turns out the Kolmogorov scale, that causes some mixing. Well, let's say this is the preheat zone. The Kolmogorov scale, that causes some mixing in here. But there's another eddy, there's a little larger than the Kolmogorov scale, that causes more mixing. So forget about the mixing of the Kolmogorov scale, okay? And then there's another eddy that's yet larger, but that can't do anything. That's too large, okay? So the eddy that causes most of the mixing, that is the one that has the same time scale, that's out of all the turbulent spectrum. That's the one that has the same time scale as the flame time scale. Okay, that is the largest eddy that can still interact with the flame. Okay, and that causes most of the turbulent mixing. And so, if you remember here the scaling relationship Kolmogorov scaling relationship we wrote earlier here today, then you can say, let's say you fix epsilon, then and you replace this here by the flame time scale, then this allows you to compute the length scale of that eddy. And that length scale will then also be the thickness of this thickened preheat zone. And it will be larger than the laminar flame thickness. Okay? So that is now, this Tm, that is now the diffusion timescale that you have. That's the diffusion timescale that you have in this modified preheat zone. Okay, so this is what we said earlier. So this was the thin reaction zones regime. If you go to even larger Karlovitz number, then you will extinguish the flame. Or you get in the broken reaction zones regime, and it is likely, not necessary, but it's likely that the flame will extinguish in that regime. Actually, it is very hard to extinguish. To blow off is simple. Blow off a premixed flame. But not blow it off, but extinguish it locally because of the effect of turbulence. That is very, very hard. Several people have tried for many, many years to generate a premixed flame that does not blow off, but locally extinguishes. And only recently, a group from Australia, Assad Masri, they have succeeded in creating such a flame. And what they do is this. They have a premixed flame, okay, goes like this, and they crank the Reynolds number up so much that it would actually blow off. But then they have a huge pilot, big pilot flame. And so it extinguishes, but then because of the pilot, it relights later on. And that pilot also, it makes it stable, very close to the nozzle. But then later on, with the effect of the pilot first, then later on, you will have extinction. So it's very hard to go in that regime and still burn. Okay, and you have to do a lot of tricks if you want to do that.
What is the physical mechanism? That's just through dissipating the hot species, basically?
Yeah, that's a good question. What is the physical? How can this? If you have burned here on this side and unburned on that side, what's the physical mechanism? And the physical mechanism, you could look at it in two ways. If you, or let's say, just one way. If you have a premixed flame here, then you have radicals that go like this. And even if this is hot and this is cold, if you just, stretch this enough, then these radicals, these gradients become larger and larger, and you lose radicals. There's too much mixing, you lose the radicals to the outside, or, if turbulence comes in, you lose the radicals, and then the radicals go to zero. And you still have hot here and cold there, but it doesn't burn anymore, because there are no radicals. Okay? And anytime you produce a little radical, you will mix it away.
So is the word model this universe compatible mechanism to predict the radicals? Because I have seen some results about this flame recently that even TDF methods cannot predict this case. I'm not aware of any other calculations.
Well, we have done calculations of this, and others have done calculations of this. This is one of the new cases that is used in this. In this workshop. What is important, we don't know yet, because this is a tough case to compute. I think you're right when you compute the radicals. I mean, for us, now maybe that goes a little bit beyond what we should be talking about here, but we have developed these flamelet models in the past, and for non-premixed, so the flamelet models, we always say, with these we talk about fast chemistry. But really, it turns out the chemistry doesn't have to be too fast. We have applied these also to ignition problems where the chemistry is really slow, and so on. You just have to, let's say, sensitize these models to these situations. The real point is that these flamelet models are multi-scale, and so they should always be able to, see what's going on in small and the large scale. Now, we have done simulations for this, and we failed to get the right results. We actually get some extinction and reignition, but quantitatively not right. This is good as a model, and this is what you want. You want to have a case where the models don't work, and then we can analyze what we need to do to these models too. And we have some ideas. And this is a very good point. Really, the key, I think, is to get the influence of the radicals. Because if you just look at a Process variable equation like we looked at earlier, a Process variable equation, that would just say again, here's cold, here's hot. It wouldn't tell you that in the middle there's no radical. And so we do have a new formulation, which I think is submitted somewhere. Maybe it's accepted even, I don't know. But that looks more, takes more of these radicals into account. I think that is the key process. Yes?
Does the regime diagram give any insights on design of combustion devices or the regime of operation rate should be uniquely designed?
I think it's so the question was, does the regime diagram tell us something about how should we design a combustor? And the answer is yes, in a sense, not completely, but then also, usually it's the opposite, okay? And I tell you what I mean by this. Yes, the regime diagram would tell you. Let's see, I'll find this again. The regime diagram would tell you, you want to have as much turbulence as possible because you want to have fast flames and fast mixing and all of that. But you don't want to extinguish the flame, which means you want to operate somewhere here. Okay? You see what I was showing? Here. This region, that's where you want to operate. Because it still burns, but you get a lot of mixing. Okay? You should not necessarily cross this line because the flame blows out. Now, that would tell you what the local L over LF is and the local V prime over SL. And then the question is, from this, can you back out what your combustor design should be? That's why I'm saying it doesn't tell you the whole story, because you would still need to say, hey, how do I get a combustor that gives me a V prime of 35 meters per second? Okay. Now, on the other hand, though, it typically is the opposite. A combustion engineer designs a combustor, and let's say they're not very good at it, and the first try, the flame blows out, and so on. They change something, and they go back and forth, and finally they find one that burns and has really good heat release also, very small and so on. And then you would locally measure U prime and L, and you put it in this stick diagram, and you would find it sits around here. Okay? That's what you typically see is all technical. That's why I say most of the technical applications are found here in this regime, not because the combustion engineer looks at this diagram and then goes off and designs a combustor, because they design a good combustor, and then, it just turns out that's what it is. But, I mean, if you don't want to do it just by trial and error, this might give you some hint of where you want to be. Okay. Yeah. Yeah. Yeah, I think you're right. I would agree with both. Maybe it helps you a little bit to scale it up because even if you use a different fuel or whatever, it would kind of tell you, well, if I have an SL that's twice smaller, I need to have a V prime that's twice smaller or whatever. So it gives you some guidance. But I agree. These diagrams are more to teach you what the physics are. To have you say, oh, the flame blew off, and you say, oh, that means, I was probably here in this regime, and that's why it didn't burn. Or you look at the combustor, and you see, it all looks so smooth and nice, which means you're probably in this regime. You can crank up the Reynolds number a little bit to get in this regime and so on. But this is more to really distinguish between the different physics that you have. So, we said that in the thin reaction zones regime, then, the reaction zone is still intact, but there's mixing in the preheat zone, and we said the thickness should be this Lm, which we determined, and then we can look at experiments here. Let me see, I'll find this again. Yeah, these are experiments that show the temperature measured in the premixed jet flame and the CH radical. CH radical, right? And the CH radical, we said, that's actually usually is a pretty good marker for where the reaction zone is. And what you see here is that the CH, it always appears in a single line, okay? Which shows you that the reaction zone here is still thin, and you don't see CH going like this. It's always, you know, one layer, which shows you that the reaction zone here is undisturbed by the turbulence. But then the temperature profile here, you see, you know, that is thickened, and in both, you know, more on the burned side and more on the unburned side. And also you see here, you know, the CH peaks here at roughly, typically around 1000 Kelvin, and that would be the inner layer temperature. So that should always peak at roughly the same temperature. And here, for example, you see a cut, and this is a cut where you just cut the flame 3 times, right? You see here the temperature is low, and then the temperature goes up. So you cut the flame once, the reaction zone once, temperature is high, and then here it goes down again, and you cut the reaction zone again, and so on. So this last one that would give you, you know, something that looks like this for you. So you go from the unburned to the burned, back to the unburned, and here again back to the burned. Okay, and here you see in this one instance here, you see, you know, there's some fluctuations in that CH profile also. That's another thing actually you should keep in mind. I mean, we talk about these regime diagrams. It seems like you were talking about, well, this flame, it will sit right here. That's not what it is. Look, you have in your real flame, you have fluctuation, local fluctuations. So if you would do many experiments, and you would always measure, you know, U prime over SL and L over LF, you would see, you know, there's a big cloud here because, you know, you have locally fluctuating conditions. And then you see sometimes it might extinguish, but most of the time it burns right. Okay, let's see what's up next. Okay, this is what we just talked about. Okay, so maybe we'll skip this part here, but in LES, there's an interesting question, and that is, in LES, what you model is below the filter scale. Okay, so the largest turbulent scale that you need to model is actually the filter size itself. Okay, does that make sense, everyone? Yeah. So we could try then to replace the. Now I need to find this regime, this diagram again. We could try to replace this L by delta, the filter size, okay? Because this is the integral length scale, but delta, that would be the largest scale we need to model in LES. Now if we do that, then this here would essentially represent the filter scale, and this the velocity scale. And then you see, what happens if I just change the filter in LES? It seems like I'm here, and now I make the filter smaller and move over here. It seems like I'm moving from one regime to the other. Does that make sense? No, because, why not? Right, the regimes, these are describe the physics, they have nothing to do with the numerical simulation. But the filter, that's a numerical parameter, really. So changing the numerical parameter shouldn't, in a good combustion model, shouldn't change the physical regime, okay? So because of that, we have come up with a different regime for LES, a different regime diagram for LES, and we use different axes here. We use this delta over LF, we use this here, the vertical axis, and then the horizontal axis here. That is, makes perfect sense, I think, if you think about it for 1 second. We said the whole time, we said the Karlovitz number, that's the most important thing. And so we use the Karlovitz number as an axis. So why did the original inventors of this diagram not use the Turbulence number? Why did they use U prime over Z and L over LF? The Borgy diagram. It's called the Borgy diagram. I think there was a similar one by Foreman Williams also, and I think he used the Turbulence number. I have to go back and look at it at some point. But why did they use the Borgy diagram? Why didn't they use the Turbulence number? It makes so much more sense. Because it was made for combustion engineers, and combustion engineers understand U prime much better than the Turbulence number. Okay, so U prime, you know, you feel that, you know, and L, integral length scale, you feel that as a turbulence, you know, engineer. But Turbulence number, yeah, I hope you guys feel that also. I do. I feel the Turbulence number. But so here, what you see then is this here is an axis where we change the numerics. Okay, we changed essentially the grid size in the simulation. This is an axis where we change the physics. And then you see, now by changing just the filter size, going vertical, you cannot go from one regime to the other. You can just, you know, within one regime. So if I'm in here in the corrugated film regime, and I make the filter smaller, or the mesh smaller, smaller, then you see at some point you resolve all the turbulence, but maybe not the flame. And if you then make the filter even smaller, if the grid size now becomes less than the thickness of the reaction zone, then we say, oh, now you also resolve the reaction zone, and this would be DNS. You see in a broken reaction zone, there's no such distinction. What's interesting then also, now if you go horizontally, you can go from one regime to the other. And this is what I said earlier. This is from an LES of a, you know, just a premixed jet flame. At one point in time, we just, in every single cell, we evaluate these numbers, Turbulence and this delta over LF, and we just plot it all here. And then you see you get a lot of points that are here in this thin reaction zones regime, but you get some points that are here. And we did another case also, we see there's also some points in the broken reaction. Okay? This is a very strongly fluctuating quantity. The spread in this direction just shows that we used the stretched mesh. Right? This is different in different parts of the world. And then you see this line here, LM. We said earlier there is this LM. That's the thickness of the thickened preheat zone. And for LES, that's an interesting quantity again, because if the filter is smaller than this, then you resolve some of these velocity fluctuations. But if the filter is larger than this, then even in that regime, the entire flame will be on the subfilter scale, okay, on the subfilter scale. And turns out that delta over LM, or LM over delta, is proportional here to the Lamprella number, to the minus 2/3 or something. And so this means that delta equal LM, that's equivalent to the line subfilter Lamprella number equal to 1. So that's what I said earlier. In LES, the Lamprella number has some meaning, a little bit of meaning. And this means that if you look at this, I go back to this experimental plot. If I look back at this experimental plot, if the Damköhler number, subfilter Damköhler number, is larger than 1, then the cell size is so large that all this change in these fluctuations, they appear only on the subfilter scale. So then still the flame looks like a jump to the simulation. But if the subfilter Damköhler number is smaller than 1, then some of this fluctuation here is resolved. Okay, so that's why. Now if you look at this regime diagram again here, this is the part where Damköhler number is smaller than 1. So here some of this is resolved, and here it's larger than 1. So in all of this regime, or in all of this part here, the flame, even the flame that's thickened by the turbulence, appears on the subfilter scale. Okay. Okay, so this is described in these following slides, which we don't need to discuss in any more detail. This here shows you the scaling I just mentioned, Lm over delta. This is equal to Duncular to the minus 3/2, 2/3 is what I said. Yeah, but that's all described here. I don't know why this appears here again. This here is at the end maybe. I want to show you how this looks like in reality. Reality in quotes, because so this here is an experiment, and you see this experiment that was done with a flame in the corrugated flammable regime. And shown here is OH chemiluminescence or something. And what's interesting is what you see here is, first of all, the flame looks like, now corrugated flammable regime, here the flame is thinner than the small scale of the turbulence. And that's what you see here. The flame appears like a discontinuity. That's just what it is from this experiment. You see a lot of fluctuations here, but the distance, when you go from unburned to burned, that's like a discontinuity. Okay? Now here's another thing that I mentioned some time back, must have been at least 2 or 3 days ago, so you might not remember it. Remember I said when you look at the curvature of a turbulent flame, because of this Huygens principle kind of a burning, you will always have very large curvature or very small curvature radius towards the, now I have to think, towards the burnt, and very small curvature or large curvature radius towards the unburnt. And you can see that here. You see here, this very large curvature towards the unburnt, and then towards the burnt. Here you see you always get these very high curvature regions. Okay? So the PDF of curvature is not symmetric because of this propagation. The propagation always forms these cusps, like what you see here in this experiment. Okay, so this here is an example here for the corrugated flammable regime. Then this here is DNS, and this is an example for the thin reaction zones regime. You see here that that you get a lot of turbulent mixing here of hot stuff. What's shown here is density distribution. So this here is burnt, and this here is unburnt. Density, you can also say it's temperature or it's progress variable. So this here is a high progress variable, this is a low progress variable. And you see that you get a lot of turbulent mixing here of the stuff from the preheat zone into the into the unburnt, and you get a thickening of this flame. Whereas sometimes here you have regions where you don't have much of this. Okay, so this here would be a region again that is more in the corrugated flammable regime, and this here is a region that would be more in the thin reaction zone regime. And then you see that finally the jump in temperature here again appears almost like a discontinuity. Okay, not everywhere, but mostly it appears like a discontinuity. And that is because in this regime, the turbulent scales, they're still larger than the reaction zone. Okay? And well, sometimes you see it's thickened, maybe here, maybe this is a point that would be more in the broken reaction zone regime or so on. And then the other thing here you see is as an example, also just as an example. So this is DNS. But let's say you would do an LES for this, then you would use a mesh that's much, much coarser. Okay? And let's just say this is the LES mesh that you would use. And then you see here in this region, you actually resolve some of this, of the temperature changes in now the preheat region that's now thickened by the turbulence. Okay, in this part, you see you have 3 cells actually here in the preheat region. So this here is in the regime here where the Duncular, subfilter Duncular number, well these are switched actually. No, they're not switched. So here you resolve some, So this is this arrow here. So this is the regime where you resolve some of it. But then here in this part, you see, you do, even though you do get some broadening here of the preheat region by turbulence, you still see from all the way from everything burned to everything unburned, that goes in less than 1 second. Okay? So that regime, the subfiltered angular number is smaller than 1, and you are more in this region. Okay? So in that sense, this diagram, it gives you some, information about, numerical requirements or for how to do a large eddy simulation.
So then you use this as a guidance, right?
Well, I mean, one thing you could do, for example, is you can evaluate these, like I did it here in this plot, and then you can draw it here, and you can see, well, should I resolve more or not? Okay, how much do I need here to, resolve, to push all of this in the partially resolved state and so on? You could do that. So this would mean here you have to change your mesh here by about an order of magnitude, right? If you want to get all this stuff here over here, you have to change it by an order of magnitude. Okay? No. See, this is what I said earlier. These scaling relations, they just look at time scales. And the chemical time scale here, that is given by, LF and D. It doesn't mean that the flame thickness is LF. That just means the chemical time scale is given by LF squared over D. Square root. Yeah, no, that's a good point. I mean, the assumption here, see, again, all these scaling arguments, they just look at, you have a flame here, and you have the turbulence here, and now I want to see how they interact. So I just look at what is the chemical time scale, and I can get that from a laminar calculation. And then I look at, or I can get it from LF and D and whatnot, okay? And then I look at, on the other hand, how does the turbulence look like? Now here, we don't consider that the turbulence actually changed by the local heat release, okay? That changes the local turbulence also. And we don't consider, in this argument, and maybe that's what you say, that if you go to the thin reaction zones regime, then maybe the chemical time scale is a little different than what it would be. Even though it's just chemistry, maybe it's a little different than what you have in the covalent thing. And that.
My question with all these scaling arguments is how you can compare something that is numerical. So numerics are governed by their own time scales, depending on how you choose some parameters, the calculations, with something that is physical that is governed with physical time scales. That's what.
Yeah, no, I don't think your solution should ever depend on what your time step was in the simulation.
Not time step, but the chemical mechanism as such, if you choose like one-step reaction or a tail, kind of implies different time scales.
Yeah. No, if you evaluate these with a good mechanism or a bad mechanism or one-step chemistry or multi-step chemistry, that might give you a different result. But
that's what I'm asking.
Yeah. No, as always, you have to try to find a mechanism that gives you something that is close to the truth. Yeah. Okay? Okay, so there's some, stuff here, I call this appendix in the, I think you have this in your handout. No, I just called, this was just old slides, so I just put it at the end here. So there's nothing that's really relevant. Okay, so we move on, and so we have talked a little bit about the physics, and then there are methods for how to now describe combustion in a numerical simulation in these different regimes. And for different regimes, you have to use your model has to know, how the turbulence chemistry interaction is. So different regimes, you might have to use different physics or different models. And we have looked at an approach earlier, the level set approach that allows you to describe the evolution of these laminar flames. Now here we'll formulate this for turbulent flames. And as I said earlier, I don't want to go into too many details of this model. I just want to tell you, some main features of the model. On the other hand, we saw that we said earlier that the level set equation, that's just a kinematic equation. Okay? It's not a conservation equation like the energy equation. Just kinematic. And but the chemistry, it enters at some point in that equation. And the way the chemistry enters in that equation, that was the laminar burning velocity. Okay? So the laminar burning velocity, that's a parameter in that equation that and it doesn't go away like in that other model I showed you. That's just a parameter that captures everything, or let's say that captures the interaction of the small scale diffusive transport with the chemistry, and these combined as combined effect that enters the level set equation. Now, when we derive the level set equation for the turbulent flow, there is a similar quantity that will appear, and that's the so-called turbulent burning velocity. So again, we will have a mean flame front position, and we will track that mean flame front position with a level set method, and that has a propagation velocity, and that propagation velocity now is a turbulent burning velocity, and that turbulent burning velocity, that needs to consider not just the laminar, the laminar burning velocity part of it. It also has to consider the flame wrinkling, and has to consider the interaction, that the turbulence has, small scale, large scale interaction that the turbulence has with the flame, and capture all these things that we just discussed, using the regime diagram. Okay? So here we'll talk about this level set approach. The next part then, lecture 13, will be all on this so-called turbulent burning velocity. Okay? Okay, so I think most of this here is actually just summarizing again what we talked about earlier. There's a scalar G, and that scalar is just a scalar that's defined in space, and we define it such that it will be 0 or G naught, some value that you want to specify. We always use 0. So it's 0 at the point where the flame sits. It's smaller than 0 in the unburned, larger than 0 in the burned. Typically, you see here we take G equal to 0, and then by that definition, then you can derive an equation that describes the evolution of the scalar G, and it describes. So if you solve that equation, then let's say for a time step, you will find that the isosurface G equal to 0, it just moved a little bit here by the combined effect of the the velocity field that moves this thing around, and the burning velocity, which leads to a propagation of this front normal to itself. Okay, and we introduced. So this is just a repetition of what we did earlier. We introduced this normal vector here, and we said the flame moves here by the background velocity again that moves things around, and the laminar burning speed. Then we were able to, by saying at this point here, G should always be equal to 0. So as long as I sit on the front, if I sit on the flame front, then the change of G should never be, the value of G should never change. Okay, which means if I sit on this thing, the substantial derivative has to be 0. The substantial derivative is the derivative of a point that moves with something, okay? And then you can write it like this, where this is the speed of this point. And you can see this is the speed of a point on the flame surface. I can introduce this here, and then I get this here. That was the G equation, where this here is the velocity condition on the undergrowth. And that G equation, that was first proposed by Williams, and then Kirstein at Sandia, Livermore, and Williams did some, DNS studies. Ashworth did some DNS studies. Look at this, and this was then later on developed into a combustion model. So the G equation, it can actually track thin flame structures that propagate with a well-defined burning velocity. Okay, so anytime the flame is, very, very thin compared to the turbulence, then it's very obvious, what this means. And that is the case. We know this now in the corrugated flamelet regime. Okay, so in the corrugated flamelet regime, you have this this equation that describes the local evolution of this front, and all you need to specify here is the Berlin cluster. And I mentioned just for numerical purposes, you have to. So the definition of how you define G, that's in a sense arbitrary, as long as it's regular. You have a regular field. But typically, I mentioned this earlier, we define G to be a distance function. So the value of G always gives you the closest distance to the flame, and that is not conserved by that property is not conserved by solving that equation. So every so often you have to do a so-called reinitialization, which means you fix the entire field again to be a distance function without touching the isosurface of G. And then you have the burning velocity, and that can actually be modified here by curvature and stretch. That's what we looked at. Some theories here for how the stretch and strain effect influence the burning velocity, and I mentioned this last time. There's here by Clavin. There's a very important paper, and here by Professor Matalon and Matkowski and Professor Matalon. He taught this course here last year, so if you were here last year, then you know all about these things. We did this, and again, this is just repeating what we did earlier. Same here, and same here. And same here, and I showed you these plots also. Just to show this again, this is the burning velocity here as function of the stretch here that is caused by curvature. And you kind of see, the only reason why I show you this is I want you to see how much does curvature actually change the flame speed. And what you see here is 250, and then here for this particular case, this is about 50. So you see, 50 out of 20%. Okay, change the burning speed by 20%. Here it goes from like 25, 35 over this range, and again, about the same thing. So it's not a huge change. That's what I want to say. Both of these ranges. You could say, well, if you make the range 5 times as long, 5 times as large, you would get 5 times the difference. But both of these are from experiments, and both of these are, kind of the ranges you can get in an experiment. Okay, so the changes by stretch and curvature, are not all at one. They are usually corrections to the laminar. Okay, and I think we looked at this also. I don't think we did this. If you just take this as and plug it into the equation, of course, here you get 3 terms here on the right-hand side. One is just the unstretched term. One is a correction by curvature, and one is correction by strain. And then you have an SL times L, Markstein number, Markstein length, and you see Markstein length, or SL times a length scale has units meter squared per second, so that's called the Markstein diffusivity. And again, this is just a definition, because it has the units of diffusivity. So this is the diffusivity times the curvature, and that looks a little bit like a diffusion term. Okay? The original equation here does not have a diffusion term, right? Finding that equation again. Here, no diffusion term. This time-dependent term, advection, and then there's a propagation term. So that equation, G equation, I missed to say that, that also has, from a numerical point of view, it has totally different characteristics than the conservation equation that you're using. So solving that equation is not entirely trivial, because it's very different. And in particular, a diffusion term in an equation is usually what makes the solution easy. The larger diffusion, the diffusion term is, the easier the solution of the equation is. Here you have no diffusion whatsoever, so that's that doesn't make it particularly easy. But and then you see here, if you plug in back these terms, then you get something that is not exactly diffusion term, but it looks kind of like a diffusion term. Okay, so that makes the solution actually a little easier. Okay, so the idea here then is this. You have a flame, and let's say that's the corrugated flamelet regime, and then you see the white line here, that would be the surface G is equal to 0, and that just follows, kind of this contour here, the instantaneous flame contour, and then you see these are other isosurfaces of G, which are, here here they must be negative, and here they must be positive. And so you have in this point here, so let's say this is one cell, and you look at what happens in one cell, you see, there's a flame in this cell. This here would be the progress variable, or the temperature, let's say, as function of G, and then you see, even though this is now not resolved by solving the G equation, you could always map a solution like this. You could map that back into the flame. Okay? So for example, if let's say this was a cell, a computation cell, and or this is a computation cell, so here you have that much surface in here, and then you would say, okay, I have a source term here for NOx or whatever. Then you can integrate over this and find what's the average source term of NOx by mapping back this 1D premixed flame solution back into this field, and you could use that then as a source term for a NOx equation that you solve. Okay, so this kind of gives you the idea how you deal with this in the thin reaction zone regime. In the corrugated flame regime. The problem though is we said earlier, well, in the thin reaction zone regime, it didn't look like this. The flame is not infinitely thin compared to the turbulence. And so in the thin reaction zone regime, the assumption to track the entire flame, or to assume the flame kind of looks like this, like a step function compared to the turbulence, that doesn't work anymore. Okay, you have something that looks different. And so in the thin reaction zone regime, we have to come up with something else. And so there is a long derivation here on how to do this, how to derive the Levitt-set equation in that regime, and I'll show you what the idea is, and we won't go through the details. But the idea is this: rather than assuming the entire flame is infinitely thin, we can say, oh, we want to track a surface, but now the temperature, field is not infinitely thin and so on. But we could still say, let's just track a temperature isosurface. Let's pick a temperature, let's say, 1000 Kelvin, and then we just derive a Levitin equation for this surface, and we track that, by a Levitin equation. Okay? And then you still need to think about, what happens away from that surface. But at least we know if we manage to derive an equation for that, then we can still see where does the flame sit as a function of time in space. Okay? So what temperature should we choose? And you see it here. Think about it for 1 second. And then of course, we choose the most significant temperature that you have in the flame. That is the temperature that you have in the inner layer, in the reaction zone. Okay? And that is the so-called inner layer temperature. And you remember still how you got that. We got that from comparing this reaction 1 chain branching with reaction 5 chain breaking, and that gave us for a fixed pressure, that gave us a temperature, and that's exactly the temperature, all the chemistry happens, and where the reaction zone is. Okay, so, and because we say the reaction zone in that regime, the reaction regime, is still thin, we can say this is here we still have a thin layer, and by tracking the temperature isosurface, we track actually the location of this thin layer, of the reaction zone. Okay? So this is showing you. Okay, so how do we do this? We say, okay, this is the temperature equation. We want to say G should now be equal to 0, at T equal to T naught, at this isosurface. So we say we sit on the flame, we sit on this isosurface and move along with this isosurface, then the value of G shouldn't change, which means again the substantial derivative of G should be 0 if we follow that surface. So dxf dt here, that would be the displacement speed of the isosurface of T equal to T naught. Okay? So it's very similar to what we did earlier, only that, now here, the temperature appears.
I think I'll just go back one step. So here you're saying it's not suitable for two reactions regime because is it because of either of the two conditions above and not being satisfied, or
No, this is because we said earlier, we say we have a step function. And that step function, that's an isosurface. Okay? And so the whole flame is collapsed to a surface, and we track this flame. But now, you see, I like this picture here actually. Oh, this was in the previous one. The experimental picture where you see CH, and then you see the temperature. Now, we can't say this is all in one layer. However, if you just look at the position where the CH peaks, that is a very distinct point. And here we want to track that point, and we want to derive an equation for it.
so if I understand you right, the issue is that the surface will not be a surface anymore. It's actually just a finite thing to it.
Well, what we originally assumed to be that surface, which is where the temperature goes from 0 to 1, that is not a surface anymore, and so we pick a different surface. That's okay. And so that surface now is this temperature isosurface, and okay, let's find this again then. Temperature isosurface. Okay. Now, what's the propagation speed of the temperature isosurface? Let's call this SD. Okay. So that temperature isosurface is first moved around just with the background velocity, and then background velocity, and then it has its own propagation speed. Now, how does it propagate? This is a reactive scalar, so it will propagate by diffusion or heat conduction, whatever you call it, and by chemistry. Okay, and so it turns out there is by Gibson here he derived an expression for the displacement speed of a scalar, in that case a non-reactive scalar. It's very easy to, to add this chemical source to. Okay? So this is what it is. It's the displacement speed, and we can plug this in here. We need the surface normal vector, which depends here on the gradient of the temperature gradient at this temperature. That's easy also. And we can replace this because the surface normal, the surface of t equal to 0, t equal to t naught, and g equal to 0 is the same. And so we can replace the normal vector here with that of g. That's a detail. But then, plugging this in is what we get. Okay? But we still don't know exactly what this means. I said I'm not going through the details here, but now I am going through. Okay, so look at this. This has two different contributions. Now you see what used to be SL is now this thing. And this has two contributions. One is this omega, and then we have this kind of a diffusion term here. Okay. Now let's look at these two different parts here. This here is a diffusion term, and that can be split up into these two terms. Turns out the first one is a curvature term. You see del dot n. That's a term that just gives a curvature contribution. And this here is a normal diffusion term. So you have the temperature and you have diffusion in some direction. And what we do here now is we say, oh, this should be our flame. And now let's look at what are the different contributions to this diffusion term. And what you see then, so let's say this is the flame. Then what you see is you get one contribution just by the fact that you have curvature here. And then one contribution is just the normal diffusion to itself. Okay? And so that's how we split it up. That was actually, that's here somewhere, I don't see it. That decomposition here is actually credited, usually, to a paper by Dr. Jackie Chen, who will give a talk this afternoon. So that's why I should mention this here, even though it's not written here. Is this not working now? No, it is, right? Yeah, okay, good. Good, so we have these two different contributions. So now we have three contributions. We have one curvature, one is the normal diffusion, and one is the chemical source. Okay? Let's see how we put this in here. And then we split this up into these three parts. You see this here now. So this here has two parts. One's curvature, I'll write this here. One is the normal diffusion, and I call this here SN. And one is the source term. I call this here S reaction. Okay? So these are the three different parts. And now, with the curvature term here, we can just keep that. That's actually very similar now to the term that we had in the corrugated flamelet regime. Except, in the corrugated flamelet regime, the diffusion coefficient was the so-called Marsden diffusion. And here, it's, just the diffusion coefficient. Okay? Okay. Then we have these two terms. See if that comes to the next slide. Yeah, this is this and this is this. Now, what's interesting is you have this temperature front, let's say. That temperature front, it propagates normal to itself just by diffusion. Okay? Look at this. I'll show you how this works. Let's say you have a temperature profile that looks like this. Okay? And let's say this is the temperature. So this temperature is a function of space, right? This is x and this is t. Okay? This is my t equal to t naught, let's say. And now let's say no chemistry. Okay, just diffusion. Then after a while, this will look like this. Right? And that temperature isosurface, it moved from here to here. Okay? So that is Sn. That's exactly what this Sn is. It's just you have diffusion. But you see, it can't go very far because at some point, you know, nothing happens. But then you have this SR. What does the SR do? Same thing. Let's just take this here now. And SR says, well, whenever I'm above this point, then I get chemistry. So it would kind of do this. Okay? And then diffusion, you know, would move this point a little further again. So what I want to say is, Sn is just a non-reactive part. That can't go very far without reaction. And Sr, that's just the reactive part, and that can go very far without diffusion. But Sn plus Sr, that's exactly the mechanism of flame propagation. Okay? And that's why we say here, Sn plus Sr, these two together, they're actually equal to Sn. Okay? Both together cause the flame propagation, and that's just Sn. So you have now, we had three contributions. One was curvature, one was normal propagation, and one was reaction. Now we say the normal propagation plus reaction, these together are just Sl, and the curvature part stays there. Okay? And that's now what's pointed out here is that of course is not exactly right. Okay? Because what we said earlier is, well, you know, this propagation actually, it is disturbed by the turbulence and all of that. And so this is actually not exactly the same as laminar burning velocity. However, we want to say that this SL now for the, you know, disturbed flame and the laminar burning velocity, they are the same, of the same order of magnitude. And so because of this, we just use the laminar burning velocity to describe this. Yes?
So I had a quick question. I think it was back on slide 25 maybe. When you did the, so that decomposition there, right?
Yeah.
So my question is, isn't the diffusion term that's on the left-hand side acting normal to the isosurface anyway?
This is acting normal to the isosurface anyway?
Doesn't diffusion occur normal to the isosurface regardless?
No, this is, it doesn't go normal to the isosurface because if you have, you know, if you have a curvature like this, then what is normal to the isosurface? I mean, what you want to say is that usually it goes normal to the, or in direction of the gradient, right? But you have a contribution here that goes normal to, that goes in direction normal to the gradient, and then you have another part that just comes from the curvature. So that actually makes the transport faster than if you just had a flat flame. And that's similar to, remember when we talked about the Bunsen flame, we said it burns fast on the top because you have curvature. And and on the sides you just have this term, which gives you then the laminar burning velocity. Yeah, that's you know, in the Bunsen flame you see it. This you just get this, but then in the top you get this curvature part also, which causes faster propagation. Okay. Okay, so so this is not exactly right. This is the laminar burning velocity, but that's what we do. Okay, so let's see what the time is. Okay, so Professor Law said I cannot let you go before 12:05. He said I have to steal you 5 minutes again of your life. So 6 minutes. Sorry about that. Let's see. I could tell you jokes the last 5 minutes. So you guys have to work this afternoon while I get to enjoy the soccer game. Anyone from Germany? You're from Germany? No.
I was born
Huh?
I'm from that.
Oh, thank you very much. Very good. Anyone from Spain here? You're from Spain? Oh, from Italy. Yeah. Anyone from Spain? No, I went last afternoon. I went back to Maroc because I wanted to work, and but then I turned on the TV and I was working actually, but watching that game with one eye. But it was a really good game, and so I think it was 1.5 eyes at the end. Okay, anyone from Portugal here? No. Okay, good. So let's get back to work here. Where were we? This here is now the equation we have. And again, it looks very similar to the equation in the other regime. Because this here is not exactly the laminar bearing velocity, but we say it's of the same order. It's very close. And this here is not the marked in diffusion, but it's the real diffusion coefficient. Okay? So this just compares these two, and then also there's this strain term here. The point though is that what we want to remember is these effects of strain and curvature in the laminar. I mean, in the corrugated film regime, this and this, they were not all that strong. Okay, they were like 10-20% or whatever. They were not super strong. Whereas we would see that this year for turbulent flame, it will be very strong because the small scales of the turbulence now, they create a lot of very strong curvature. So this term here, the thin reaction term, is actually very strong. Okay, so yeah.
Going back to the third top equation, would it be correct to say that S sub LS minus E minus kappa is the same as the equivalent coefficient of the
These two together are this? Is that what you're saying?
Yeah, would that be correct?
No, because these equations are not the same. They're not meant to be the same equation. One is an equation that was derived for certain physics, the corrugated flame regime. And the other one was derived for totally different physics in the thin reaction zone regime. Okay? And it turns out that we call this here DEL, but really it was SL times the Marston length and so on. And this is a kinetic parameter. This is different from this. These are different. Okay? Yeah. Because also the flame and the chemistry has a certain receptiveness to curvature, because of all of the above, and that's expressed in the Marston number or the Marston length. And so this is not a real diffusion coefficient. It's just something that has dimensions of diffusion coefficient. This can be even negative. I mean, this doesn't even have to be positive. And so these are different. And here this strain effect, it just didn't appear. It must be hidden somewhere in here. Okay? But what we want to say next then is essentially, forget about these two terms. Okay? Next thing we'll do is we derive an equation that's valid in both regimes. Okay? We'll do this tomorrow. But essentially what we'll do is this. We say, forget about these two terms because they're not all that large anyway. Okay? And then we say these two are the same. Okay? So that's good. So then up to here the equation is the same. Then we say we just add this term. Why can we do that? Because this term is not very large in this regime. It's actually 0 in this regime. Okay? Otherwise it would appear here. It's not there, but it's very strong in this regime. So adding this term doesn't harm the solution in this regime because it's small anyway. But it will be important in this regime. So this equation here, actually we will see, that is the equation that also holds in both regimes, where we have to remember, we neglected these two, or let's say, you could say we replaced this by this, but again, these are not the same, and they're totally different effects. But we neglected these two, and we deal with the, or we accept the fact that this here might not be totally zero, even in the corrugated flame regime. So these are small mistakes we make. But we'll see then tomorrow that if we do an asymptotic analysis and say, how does this equation look like just in this regime or just in that regime, we recover these equations with that. Okay, so I was filibustering long enough, 12:05, so I let you go and see you tomorrow.